Next, I will introduce Alexnet. I think Alexnet is the first modern deep neural net architecture because Lenet is very small and it is more like a toy example. Alexnet was the champion in ImageNet 2012. It has several features. It has 5 conv layers and 3 fully connected layers, so there are 8 layers in total, and it was fairly large at that time. And experiments show that the performance gets worse when any single layer is removed. That makes sense because usually the deeper the model is, the better result we could get. It provides some fundamental structures of the modern deep neural network. It provides the conception of group convolution. Why is that? Because in the year of 2012, the GPU memory is very small. The ImageNet data is very large, and one single GPU couldn't handle all of them. So it's used 2 GPUs. It provides group convolution for the very first time. It separates the feature map into 2 groups, that is 2 GPUs. When we have group conv, we will need to take care of the intra and inter GPU connections. So what is calculated under the same GPU? It is the conv operations. They are done under the same GPU. And what operations are calculated under different GPUs? When we consider global information, we need to get information from 2 GPUs. For example, max pooling. We couldn't just get the max pooling of one single feature map in one GPU. We need to get the whole feature map from both GPUs. For example, if we have an image of a cat, we can't just do one max pooling for the cat's head and then another max pooling for the cat's leg. We should connect all parts of the cat and then do the max pooling. So we need to merge the feature map into one GPU and calculate max pooling on one GPU. Also, for the fully connected layer, if we have them on 2 GPUs, then the FC information is partially lost. So for fully connected layer, we also need to merge the 2 parts into one and then do FC on one single GPU. So this is the inter-GPU interactions. And Alexnet is the first one to use multiple GPUs, first one to use group conv, first one to use ReLU, first one to use max pooling, first one to use dropout. And these features are still widely used in our current DNN architecture designs. Local normalization is also proposed by Alexnet for the first time, but is not as commonly used as the rest now. It is hard to believe that this model was born in 2012 and is still defining the basic concept of our current DNN model architecture since it was a very long time ago. Even though we can see a diversity of architecture designs nowadays for DNN, it is still based on the Alexnet architecture and basic concepts. This is the source code of Alexnet. There are 5 conv layers and 3 fully connected layers. Note that it is a bit different from the original design. For example, if we take a look at the first conv output channel, it is 48 times 2, which is 96. But here in the source code, it is 64. So if we calculate the size of the feature map in this layer, it should be 224 minus 11 plus 1 plus 2 times 2 and then divided by 4. It should be 54 something. So if you get the round of it, it is 55. And note that the group size is not specified here. The default value is 1. So if you use PyTorch Lightning, you do not need to set the GPU explicitly here. And if you see the FC layer, for the input dimension, it should be 256 times 13 times 13. But here you can see that the input dimension is 256 times 6 times 6. Why is that? Because before it has an adaptive average pooling. So usually in average pooling and max pooling, you essentially set the stride and kernel size by your own, setting them as hyperparameters. You will have to reconfigure them if you happen to change your input size. But in average pooling, on the other hand, we specify the output size instead, and the stride and kernel size are automatically selected to adapt to the needs. So here you can see that in features, it has 1, 2, 3, 4, 5 columns. And in classifier, it has 1, 2, 3 full layers. And in the forward function, we first calculate the 5 column and then get the adaptive average pooling, and then we flatten the feature map into one dimension, and then we feed it into the classifier, and we finally get the output. Note that if you take a look at the code here, they are pretty repetitive. So it's conv, relu, max pooling, conv, relu, max pooling, conv, relu, conv, relu, conv, relu, max pooling. So it seems a little bit redundant. Later on, I will introduce another network that will introduce unit to shorten the coding.